The natural exponential function is the exponential function with the constant e. Now, in class, we did an investigation of where e comes from. It's a constant, and we found out that it was approximately 2.71828284590 It's an irrational number, so it is a non-repeating, non-terminating decimal. You can find e on your the number e on your calculator is the second function above the division key. If you want to take e and raise it to a power, that's the second function above ln. So there are two different e's on your calculator. The number e is the one above the division key. So if you want to, for some reason, remember what the decimal equivalent of e is, you can press second division sign and it'll pop up on your screen. If you want to use e, you're going to use second ln. The natural exponential function is the function f of x equals e to the x, where e is the base. We just usually call this the exponential function, like any other exponential function. Now, using e is very easy if you want to just talk about evaluating powers of e and say, what's e to the third? So you shove it in your calculator, and it spits out 20.08554. There are more numbers, but we're rounding. If you want to know what 2 times e raised to the negative 0.53 is, you just do 2 second ln, and then in the exponent put negative 0.53. And then that'll spit out to you 1.17721. And then if you want to find out what e to the 4.8 is, shove into calculator, spit out answer 121.51042. Pretty easy. Now, what does the graph of e look like? Well, the graph of e is going to be like any of the rest of our exponential functions. It's going to look something like this. Because the base is a number that's greater than 1. And we found out when the base is a number greater than 1, the graph is going to go up from left to right. Remember that because e to the 0 is 1, like anything else to the 0 power, it's going to pass through the point 0, 1. That's its y-intercept. There is no x-intercept because the x-axis is an asymptote. The graph gets closer and closer to it, but it never touches it. The domain is all numbers. And the range is y is greater than 0. Let's do an application of a problem that would use e. An infectious disease begins to spread in a small city of population 10,000. After t days, the number of people who have succumbed to the virus is modeled by the function v of t is equal to 10,000 divided by 5 plus 1,245 e raised to the negative 0.97 t. How many infected people are there initially at time t equals 0? Well, think about that. If you plug in 0 for t, e to the negative 0.97 times 0 is going to be e to the 0, which is 1. You're going to be left with 10,000 divided by 5 plus 1245, which is 10,000 divided by 1250, which is going to be 8. So at the very beginning, there are 8 people who are infected. Well, now we want to know how many people are infected after 1, 2, and 5 days. That means we're going to plug in 1 for t. When you do this in your calculator, put the denominator in parentheses. Now, most of you probably have the new operating system, so when you do e, you should have no problem putting this into your calculator. Just make sure to get out of the exponent before you close the parentheses. So you'll find out after 1 day there'll be 21 people infected. Plug in 2 for t. 10,000 divided by 5 plus 1245 e to the negative 0.097. Oops, not 0.097, just 0.97. Let's get rid of that. I wish I had an eraser function on here, but I do not. 0.97 times 2 is going to be 54 people. And after 5 days, if you plug in 5 for t and plug this into your calculator, you're going to find out about 678 people are infected. So it's spreading rather quickly. The last one says roughly how many people eventually get infected. Well, the best way to figure that out is to plug in a very large number for t. Because eventually what's going to happen is that it's going to kind of level out, after which you don't have more people getting infected. So the way that I like to do the problem is I like to plug in 100,000 because it's a pretty big number. So I'm going to do 10,000 divided by parentheses 5 plus 1245 e to the negative 0.97 times 100,000, and then close the parentheses. Now what you're going to find out is that it ends up being about 2,000. So eventually 2,000 people will be infected. In the last section, we talked about compounding interest, and the formula for compounding interest was this. This is the formula we're going to use when we compound interest annually, semi-annually, quarterly, monthly, daily, hourly. But there's another type of compounding called continuous compounding. Oops, I can't even spell. There we go. Continuous compounding is the formula A equals PE to the RT. P is still the principal, R is still the rate, and T is still the time. But we use E instead as the base. I call it the PERT equation because it looks like it spells PERT, like the shampoo. We're going to use this to evaluate a problem. So let's do an example. Let's find the amount after 3 years if $1,000 is invested at an interest rate of 12% per year compounded continuously. Well, the way this is going to work is the principal is 1,000. E to the rate is 0.12 times the time is 3. And then we're just going to plug that in our calculator. So we find out that we're going to have $1,433.33. Now I want to compare this answer to compounding the same amount hourly. So I'm going to go back and use the other formula. The principal is 1,000, 1 plus the rate divided by, if you compound hourly, there are 365 days in the year, 24 hours a day. That would be 8,760 hours, raised to the 8,760 times 3. If you plug this in your calculator, what you end up finding out is that you end up with the same amount of money. Compounding hourly is very close to compounding continuously.